Welcome. I'm very pleased to welcome Carlo Rovelli, who's a professor of physics at the University of Aix-Marseille. He works in quantum gravity. He has published several books, a monograph on quantum gravity, and most recently, 7 Brief Lessons in Physics, which is a popular, accessible book to what Carlo takes to be the central insights from various aspects of physics. So, Carlo, welcome.
Thank you. Thank you very much.
So the first question with which we should start is probably, why do we need a quantum theory of gravity in the first place? GR is a very successful, well-confirmed theory in its domain. There seems to be no empirical data that clearly and obviously points to the need of a quantum theory of gravity. So people might ask, why do we need a quantum theory of gravity?
Yes, GR is extremely successful, never contradicted by data so far, and it seems to describe the gravitational phenomena very well. I think the main reason I see for looking for a quantum theory of gravity is that there are real phenomena in the universe which we are incapable to understand or to predict what might happen because of a limitation of generativity. The simplest is black hole collapse. It's we expect them to slowly decay and some way to disappear. We have no way whatsoever to see, to predict, to understand what's going to happen in the future of a black hole. So there is an obvious limitation in the picture we have of the universe. The basic laws we have about the universe, they don't cover some phenomena that should happen. More in general, I think that there are general reasons for believing that the picture of the universe we have so far is incomplete because it doesn't stay together. Generativity is coupled to matter. Matter is quantum, and a theory of classical field like GR coupled to quantum matter does not work. So we have a basic set of equations for the world that only work sort of in patches that don't allow us to understand what's going to happen in some situations, and which are clearly missing. And this is far more enough of the motivations for trying to look for this theory.
So in trying to formulate a quantum theory of gravity, given that there's no obvious empirical guidance, what should be our guiding principles and the methods we use in getting to find the vantage points and the methods to find such a quantum theory?
I think that the teaching here comes from history. Physics have made great steps ahead in the past in situations where with new data, obviously, but also in situations without new data. Copernicus is an example. There was no new data. Einstein was an example. Generativity, there was no new data, and so on. So there were various cases in which physics is capable of going ahead, making major steps, understanding open questions without new data. And usually in those situations there was a case like today, namely two well-established theories, well-confirmed, and some apparent incoherence between the two. So the data are the two theories, in a sense, and the work is a work of the theoreticians that take in this data and see how they fit. So taking the two theories and see how they fit. So we have a lot of indications of how quantum theory of gravity should be. It should be a quantum theory and should give gravity, which means a huge amount of constraint in this theory. In fact, the problem we have is not problem of richness. We don't have a lot of coherent, consistent, final, clean theories of quantum gravity, and we don't know which one is the right one. We basically have known completely coherent, finalized. So I think if we find one,
start out in our construction of quantum theory of gravity from general relativity, which is our best classical theory of gravity. What do you take the central insights, the sort of the lessons and principles in GR that we should generalize or use to move to a quantum theory of gravity?
I think with generativity we have understood that what we called space-time before, it's the same thing as a field, as a physical field, as a gravitational field. Or if you want, that the gravitational field is space-time. So we have, this is something I believe we have understood about the world. It's not going to change. We're not going to go ahead in our understanding of the world, splitting again space-time from the gravitational field. This means that after generativity, we don't anymore describe the world as a fixed space-time, things happening over it. And I think we're not going to go back into that. Like we're not going to go back in a theory in which the Earth is the center of the universe. These are things we understand. And once we have understood them, that's forever. I mean, water is oxygen and hydrogen. That's forever. The gravitational field is space-time. That's forever. So we have to put this together with quantum mechanics, with quantum field theory, which so far is formulated on a fixed space. So we have to rethink quantum field theory to make sense not on a fixed space-time, but on a quantum space-time. And we have to understand how this space-time can have quantum properties. So I think, in my opinion, the physics behind the quantum gravity is more or less intuitively clear what it should be. The problem is to write a mathematical structure that makes it concrete and to clarify the conceptual problems that are born from there.
So the approach to quantum gravity that you favor and that you've helped to articulate is loop quantum gravity. Can you explain what the main starting points or the main principles of loop quantum gravity are?
Well, first of all, it's an approach of quantum gravity which does not assume that the unification problem, the problem of describing all forces, all particles, everything in nature in terms of a single theory, has necessarily to do with quantum gravity. Split the thing. So I personally don't believe that we're at the end of physics and in reach to the final theory. We have to take one step at a time. So understanding the quantum property of space-time, or how to do quantum theory on a quantum space-time, it's a problem complicated enough that I expect it could have its own solution, even if we don't yet have a final theory unified of everything. So first of all, loop quantum gravity is that. It's a quantum theory of a gravitational field which interact with matter, but not necessarily unified with matter. And what it does essentially is to write a set of equations that describe a quantum theory in the standard way in which is done a quantum theory, so technical Hilbert space operators, solution equations, that in some classical limits give generativity. In this classical limit, space-time emerges, like electromagnetic field emerges from the photons in the classical limit, but in the theory itself, there is no space-time to start with. There is this quantum state of gravity. The current achievement of the theory, the current status of the theory, is that the mathematics is pretty well defined, and some good indications that give the classical limit have been found, exist. So the focus now is mostly to complete what is not clear and look for empirical support of this theory.
Right. So, so what's this quantum state of the gravitational field according to loop quantum gravity? Can you describe that a bit?
Yes, because there is a main physical result in the theory which is very similar to what happens in the quantum theory of the electromagnetic field. In the quantum theory of the electromagnetic field, the main physical result is that energy is quantized. So when you receive light, you receive in packets, which are the photons. So the photons, the quanta of light, the grains of light, are the main physical prediction of quantum Maxwell theory. So here the same happens. If we measure geometrical quantities, space quantity, like length, area, volume, what the theory predicts is that the outcome of the measurement, what we see, what we perceive, the way we see space-time, are quantized, so are discrete. So in particular, this means that there is a minimal size. There's no physics beyond size, which is Planck size, of course, a small granular structure of the world. So the states, technically they're called spin network states, which form the basis, which form the way quantum gravitational field is described, have a distinctive, discrete structure. They're little atoms of space connected to one another, forming a net, which are called spin networks in technical terms. And these are like the photon states. So these are the elementary elements out of which space-time, conventional space-time, emerges when I see them from very large distance, and I don't see any more the granularity.
So you said that there was some understanding of how space-time, relativistic space-time, could emerge from these spin network states. So what is your way of explaining that or making that more precise?
This has been one of the main focuses of the work of the last years in the theory. In fact, there's a huge body of work. There's a construction of coherent state. There's a construction of states that represent similar to Minkowski space, to vacuum. Intuitively, it's pretty easy. It's like a T-shirt is a continuous two-dimensional structure. But if I look in the small, it's actually threads. It's actually weaved by a thread of elementary things. So there's no T-shirt beyond the scale of the whatever, tenth of a millimeter or whatever. So similarly, space-time emerges by the weaving of these a lot of these elementary atoms of space, sort of attached and intertwined to one another. This can be done precisely in the mathematics. So one can write quantum superpositions of these elementary granular states, which, when tested at large scale, behaves precisely like classical space-time general relativity. This is very similar to what happens in electromagnetism. If I have an electromagnetic wave, I treat it as a continuous thing, but I can view it at a deeper level as a particular superposition of photon states, and we are capable of writing down exactly the mathematics that describes that. The mathematics is very much the same. Here, those the photons live on space-time. Here, the grains don't live in space-time. They are themselves space-time. They make up themselves space-time, with many of them.
So we recover a four-dimensional continuum structure in that limit.
Yeah.
You can see how that's
exactly.
that works in general.
Exactly.
Okay. There's a remaining incompleteness of the theory concerning the dynamics in some generalized sense of that term, and there's various ways of thinking about how to fill that gap.
Yes.
So how do you think of the problem, and what's your favorite way of addressing
there
it?
are two main directions to write the dynamics of these states here, which are the Hamiltonian framework, sort of a la Schrödinger equation, and in a sort of covariant framework, a la path integral, a la Feynman, summing over histories. I've worked in both at length. Recently I focused on the second one because it seemed to me much easier for actually using the theory for doing calculation. The status is that there is a well-defined definition of the covariant field. So there are some amplitudes which are written down, some sum of integrals, some clear expression. It's not too complicated, but it's complicated to work with. Mm-hmm. A lot of questions remain open, like dynamics is given in some perturbation expansion, so the behavior of this perturbation expansion is not really under control. So term by term, the amplitudes are finite, but we're not sure they converge in some, even in some weak sense, we're not sure they converge. Mm-hmm. So a lot of questions are open in whether the theory is really fully consistent and whether it fully gives general relativity the appropriate limits, and various people are working on that from a mathematical perspective. In a sense, this is a work which might be without end, right? Because even our good theories, we are not sure if they are totally coherent. I mean, quantum field theory, still ill-defined in spite of the. So I would say what is really important to see if the theory is good is not so much to keep going, cleaning up the mathematical detail and the convergence and all that. What is important is testing it.
Right. So how could you test loop quantum gravity?
That's what many of the people in the loop quantum gravity community are doing. The loop quantum gravity community is large. There are a few hundred people working on that, and quite a number of the groups, or at least the big groups, shifted from the formal mathematical construction of the theory to the utilization of the theory, saying, well, I mean, let's suppose it's finished, is good, or we can always go back and change things if necessary. But let's use it and do something. And there are two main directions. There are several directions, but two main directions which are being searched. One is cosmology. Apply the theory to early cosmology and try to see if something can be computed which can be then seen in the CMB, the cosmic background radiation. There are many papers, there are tentative steps of seeing, well, in the large angle size of the spectrum, there should be a certain tilt which can be predicted. There's a large body of work going in this direction. Nothing conclusive at the moment. And then there is the other direction, which I myself find the most intriguing, because we might have already seen something, which is the possibility of the black holes exploding, the black hole explosion. So a possible quantum gravitational phenomena, this I think is pretty clear, is that a black hole might explode, might tunnel out from itself. This is not Hawking radiation, it's a different phenomenon. And the relevant question is, how long does it take? Does it take time enormously long, so it's totally irrelevant, or does it take a relatively reasonable time? And using the theory, using the quantum gravity, one can compute this time.
Mm-hmm.
So the calculation has been done within a certain approximation scheme, and it seems that the time is relatively short, which means that black holes created at the beginning of the universe could be exploding today. So this has been computed, the wavelength, the signal of black holes exploding today, and it turns out, quite surprisingly, that is pretty similar to wavelength of mysterious signals which are observed from the sky, which is a fast radio burst. So then here is a possibility that perhaps the fast radio bursts that are impulsive signals observed by radio telescopes, so we are in the millimeter wavelength, could be exploding black hole, could be a quantum gravitational phenomenon. Mm-hmm. We're not sure, it's an hypothesis. In principle, with more observation, there's a way to test this hypothesis. If the hypothesis was confirmed, we would have a quantum gravity phenomenon directly observed, and a theory of quantum gravity which allows us to actually compute it and explain it to us.
Well, that would be a major accomplishment, of course. Now, the question, though, is that are there other alternative explanations that would get you the same radio wave signals that are so far mysterious, you said? So does that mean there are no other alternative explanations?
Yes and no. The signals themselves might have other explanations. In fact, in the literature there are other attempts, totally different, to justify that. Right. But the theory, the quantum gravity theory, predicts that this fast radio burst have a very peculiar dependence. The observed wavelength depend on the distance in a very peculiar way that no other phenomenon would have. So right now we have no way of saying which one is the right explanation. But as soon as the astronomer have a sufficient number of observations to give some statistics and see how the signal coming from far away, how the wavelength change, it would be possible to distinguish which explanation is the right one. So there is a very precise sort of smoking gun. And the prediction of quantum gravity is that the dependence of the wavelength from the distance is not the standard one given by cosmological redshift. It's corrected by the fact that black holes exploding far away are younger because they exploded a long time ago, and since they are younger, have a smaller mass, and since there's because the lifetime depends on the mass, and since they're smaller mass, they're smaller, and so the emitted signal have a smaller wavelength. So this corrects the redshift and would give a curve, which would be a smoking gun, saying yes, this is. And I would say reasonably no other phenomenon that we know could have that curve.
Okay.
So if in the best possible hypothesis, which might work or not work, within a certain number of years, we would say, look, there is that curve, there's one predicted by the theory, these are exploding black holes, this is the quantum gravitational phenomenon.
Okay, but it would require that we would be able to correlate these frequency bursts, the signals with the distance, and have enough data points.
And have enough data points, exactly. And this is in the microwave, so it's millimeters, centimeters, and there it's the astronomers know how to estimate the distance quite well independently, because the intergalactic medium is dispersive on this wavelength. So from the dispersion of the signal, they get a distance. So it's not impossible. It's within reach. We'll see.
It's just that we don't have that many data points.
We don't have data points yet.
Okay. Quantum gravity, it's been argued, has, as a field, a number of implications for philosophy, both, of course, for the metaphysics of space and time, but also for scientific methodology. For instance, some have argued that quantum gravity and the fact that the scales at which quantum gravity operates are so vastly removed from the scales that we can directly probe so far, we have to find new empirical or non-empirical methods, I should say, of theory confirmation. So we have to adapt our scientific methodology to that situation. The metaphysics of space and time is clear that there's, all approaches to quantum gravity will revolutionize our understanding of space-time and therefore have implications for that. I would like to invite you to give us a little bit of a sense of what you take to be the most interesting and most promising or most fascinating philosophical implications of research in quantum gravity.
So the two questions here. One is about non-empirical confirmation and the suggestion that quantum gravity forces us to rely on non-empirical methods of confirmation. I couldn't disagree more. In fact, it's the other way around. We have non-empirical evaluation of theories, obviously. We take a theory seriously. We believe one possible in the likelihood of success of one direction of research rather than another, very often for non-empirical reasons. Just look at the history of physics. Copernicus did what he did for totally non-empirical reasons, and Einstein largely the same. But this has nothing to do with confirmation. Confirmation is empirical. That's the strength of science. It's not going to change. There's nothing in quantum gravity that might change it. In fact, it's the other way around. Precisely because quantum gravity requires a sort of larger conceptual jumps, then we are more on the risk of being blinded by our prejudices. That's exactly what non-empirical confirmation would exposes us to. So we have to test the theory before even beginning to say that we believe is right. So I have a lot of confidence in the quantum gravity. I dedicated my life in it, but I would ever imagine to say that it's confirmed. It's not confirmed. It's going to to be confirmed when it's going to have new, genuine phenomena predicted and seen.
But would you maybe accept a weaker statement that non-empirical considerations of evaluating theories are still important?
Oh yeah, absolutely.
Okay.
Absolutely.
So
they are, and they guide us in quantum gravity, and as they guide us in all of science.
It's just that they don't give us confirmation.
Yes.
Okay.
And it's true that somehow, I guess, modern philosophy of science has told us there's no sharp distinction between confirmation. I mean, you have a sort of Bayesian view of evaluation of the credibility of a theory is not black and white, but be- but there's a huge difference between having hints about something being perhaps a good idea to explore, and believing a theory, relying your life upon it. I mean, building a machine and going into the airplane, believing that it's based on an equation that you trust. There's a huge difference. So, non-empirical arguments give us this, 2% or 3% or 5% that we need in terms of Bayesian probability to explore something. They have nothing to do with the 99% that we need when we start to say, okay, now we have understood.
Right, okay, very nice. And what about other philosophical implications or lessons we might learn from quantigravity about how the world is like, or how we should do science?
I think that the interesting part is about space and time. Physics has repeatedly modified our conceptual understanding of space and time. It did it with Newton, it did it with Galileo, it did it with Einstein. In fact, it did it with Aristotle before that, perhaps with Anaximander before that. So we keep learning that the structure of the world is different, and we see it better and better and more. And no doubt quantum gravity is going to do that again, and very strongly. Standard space and standard time disappear from the theory, which I believe is not going to be dramatic. We just have to learn how to think with weaker notions of space and weaker notion of time. And this is fascinating because it helps us making one further step in understanding what is time, what is space, what is the time and space of our experience, and what is the time and space in the fundamental grammar of the world, which might not be the same thing.
Okay. So now going in the other direction, rather than from physics lessons into philosophy, do you think there's a way in which philosophy and philosophical methods or philosophical thinking can help develop and accomplish progress in physics?
Yes, I do. And once again, history teaches here. The influence of philosophy on the development of science and physics in particular has been immense in the past. I don't think it will be possible to imagine Heisenberg or Einstein or Newton without the strong philosophical influence that they had. Some cases like Heisenberg is blatant. And this is going on today, in the good and sometimes even in the bad. I think that part of the sterility of modern physics is having absorbed some lessons from philosophy of science, which perhaps are not very good for the development of science.
Is there anything specific you think about?
Yes, the physicists have taken Kuhn too seriously. So the idea that the only thing you save from one theory to the next one is its empirical content and not his qualitative content has been taken too seriously by the physicists. So now the physicists start to explore random theories. Why not this? Why not that? And this is sterile because that's not the way science advances. Science advances either because you have data or because you base on what you know, you try to make things more clear. It has never advanced by trying randomly one solution or the other solution, because there are too many solutions, because we don't have enough imagination of finding the right one. More than that, somebody said that a scientist never does anything unless a philosopher gave him permission before. And I think it's true and deep. Philosophy is much wider as a way of thinking, and it frees thinking from it helps freeing thinking from prejudices, allows us to see where we are making ungranted assumptions. Philosophy can offer a lot of things to science. Can offer methodological awareness. Scientists have their own methodology they think is absolute until they read a little philosophy and they realize that things are much more
and can just offer inspiration. I mean, in my career as a scientist, I realized that reading David Lewis or I don't know, Hugh Price, to say somebody recent, has opened new way of thinking about things. Coming to a conference on philosophy of physics, I do learn, and each of the things I do learn are gonna play a role in the way I view my own work and in the way I view the physics, and that's how new ideas then come up.
Well, Carlo, thank you very, very much for your interview, for taking the time to talk to me.
Thank you very much.
And I'm very grateful. Thank you.
Wonderful.
Thank you.